let's see what other kind of vector spaces, or at least a few there are besides just the your standard Euclidean n-dimensional space with standard addition and scalar multiplication, right? And that's the first, or the 0th example here maybe, is Rn. And this comes with, just your standard vector addition and scalar multiplication. Again, remember, I'm going to just shorthand notation here. When I mean Rn is a vector space, what I really mean is it's Rn equipped with a certain or a specified addition operation and scalar multiplication operation, right? But that's understood in the context. So I'll just write Rn here. And we've seen and proven that this is a vector space without even knowing it. If you remember back when we were studying, we were going through calculus 3 again, a lot of the notions from calc 3, but in dimensional space instead of just 2 or 3-dimensional space, right? And we were proving all these properties that Rn is closed under vector addition, things like this. We were inadvertently proving that Rn is a vector space. Another thing that we've inadvertently proven is a vector space is the set of m by n matrices. So we'll denote this as the blackboard m and then subscript m comma n. This is the set of all m by n matrices, right? i.e., this is a collection of, the collection of matrices A, A11, blah, 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 A1n, AM1, AMN, pardon me, such that, Aij is an element of the reals for all ij between, I1 through n. Well, I'll specify. For all I 1 through m, and then for all j 1 through n, right? Understanding this the collection of m by n matrices, along with, right, what operations do we have on matrices? We've proven matrix addition. We've proven all the properties before, right? We've shown that if you add two m by n matrices, the result is an m by n matrix, showing it's closed under matrix addition. We've shown if you scale a matrix, an m by n matrix, well, that's still an m by n matrix. We've shown that it's closed under scalar multiplication, right? We've shown all this inadvertently. And so we have that this space is, this collection of matrices is actually a vector space. And this space is not all that different from Euclidean space. And let's think about why here, just for a moment. When you have an m by n matrix, so let's say A is, what we've written, like A11 through A1n, blah, 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 through AM1 through ANN, right? Each of these are an element of the reals, right? And so what this is the same as, we write it in a, we specify rows and columns and everything, but really what you could do is just write all these numbers, or take away the notion of these numbers being entries for a matrix and just think about the collection of these numbers, right, as a set, so you have like A11, A12 through A1n, and how many elements are here, right? This was from the first row. This is n elements. And then what do we have next? The next row would be A21, A22, blah, 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 through A2n. This would be another copy of n elements, right? And not only, so I'll say n elements of the reals. right? Because each of these are real numbers. You could do the same thing for 3, 4, whatever, so dot, dot, dot. And then lastly, you would have AM1 through AMN. And that would close our list of all these numbers, right? Well, and then you can see, again, this last one here, and all rows that we've placed in between, these have n elements of R. And so really, what do you think about when you think, if you have like x1 through xn, and each xi is a real number for all I, well, then you just think of that collection as being an element of Rn, right? And so what we have here is we have this collection of real numbers, but how many do we have? Well, we have m copies of n elements, which means this collection is an element of R to the m times n, right? And so really, this space is actually isomorphic to R to the mn, right? And so it's not all that different. It's not really a new example, right? Because you can think of these collections of numbers just being, like an ordered pair or something. So showing this isomorphism would also prove it's a vector space because we know R to the mn is a vector space. Now let's look at a new set and see if we can determine if it's a vector space or not. So what I'm going to do, so here's a new example, is let's define the set P2. This is going to be defined as the set of all polynomials with real valued coefficients such that well, let's not say that for now. With coefficients, with real valued coefficients and degree of at most 2. Okay, so that's a very long-winded way of saying constant polynomials, linear polynomials, and quadratic polynomials with real valued coefficients, right? Let's write this mathematically here. So P2 is defined to be the set of polynomials, let's say a0 plus a1x plus a2x squared, such that a0, a1, and a2 are real numbers, right? These may be 0, right? So you could have constants or purely linear or purely quadratic or whatever. So this is all polynomials of degree at most 2. Now, I claim that P2 polynomial addition and scalar multiplication is a vector space. Right? Let's prove it. So how do we prove something is a vector space? Well, if you remember, we have to show that the addition and scalar multiplication operations satisfy their respective list of axioms, right? So let's start with let's prove first. We show plus satisfies the plus axioms. Okay, and so what was the first one, right? The first one we needed to show was that the set P2 is closed under vector addition or closed under addition. So what we need to do is we need to start with 2 elements of P2. So let's let P of X, this will be A naught plus A1X plus A2X squared, and Q naught, or Q naught, QX be B naught plus B1X plus B2X squared, right? Or, so these are two elements of, you know, P and Q, these are elements of P2. And now we need to take their sum, and we need to show that the sum of these things is also an element of P2, right? Well, how do we do that? We have to show that the sum of two elements is also of the form that we see here, right? Something like this. And maybe to avoid confusion, since you may say, like, since I'm using A naught, A1, A2 here, and then an example, let's just say A, B, C, and then, so A, B, C is an element of the reals, right? And now, just so there's no possible confusion here, right? We need to show that the sum, so like, is P plus Q of X equal to A plus BX plus CX squared for some ABC, right? That's the question. Well, let's find out. First, we take P of X plus Q of X, and that is A naught plus A1X plus A2X squared, and then plus B naught plus B1X plus B2X squared, right? And now we know how the addition of polynomials behave over here. We know that, so like, you know, like I was saying here, we're trying to prove that it's closed under addition for this sum, right? This is a different addition, right? That we already know how it behaves, right? We know if you take, you know, these are all real valued things. We know how addition works in the reals, right? This is addition over here. This is addition for this polynomial space. This is addition over the reals. We can use properties of the reals being a vector space to show that P2 is a vector space. And so because of that, we have all of our standard rules on the right-hand side here, right? We have commutativity, associativity, blah, 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 once it's expressed explicitly in terms of real numbers. So what that means is we can write this as A naught plus B naught plus A1X plus B1X plus A2X squared plus B2X squared. We also have distributive property for real numbers, right? So this is, well, I won't use it here, but this is like, I'll group these, A naught plus B naught, and then this would be plus A1 plus B1 X plus, and then A2 plus B2 X squared. This is of the form, right? If you were to take A naught plus B naught to be A, A1 plus B1 to be B, A2 plus B2 to be C, then this is of the form that's required to be an element of P2. So this implies, well, I won't write it here. I'll just say, I'll just circle it, you know, I mean, this is an element of P2. And these were arbitrary. That means this holds for any element of P2, and so it's closed under addition, right? What do we need to show next? Next, we need to show that it is commutative. So we need to show that if you take P of X plus Q of X, we want to deduce that that's the same as the reverse order. So what is P of X plus Q of X, right? Well, this is A naught plus A1X plus A2X squared plus, sorry, I'm gonna have to write on the second line sometimes, plus B naught plus B1X plus B2X squared. And again, we don't know about the commutativity of the addition operation for P2, but we do know about the commutativity of the addition operation for the real numbers. There we have the commutativity property proven, and we're very familiar with that property, no problem. So we would have to use that a bunch of times, and what you will end up getting, right, is you'll end up getting B naught plus B1X plus b2x squared plus a naught plus a1x plus a2x squared, which is q of x plus p of x. So we've shown that this addition for P2 is commutative. And this may seem trivial, but it's not, right? I mean, yes, it's still the sum, but that's a different operation than this sum, right? The P2 sum is defined or behaves in terms of the sum over the reals, right? But a priori, we don't know that it behaves the same, right? And so we need to show that. We have to make sure that we can show that. What next? We need to show associativity. So we have P and Q. Let me define R of X really quickly to be, let's just say C naught plus C1X plus C2X squared. Okay. Then to show associativity, right, we need to show, well, if we take P of X plus Q of X first, the order doesn't matter here, and then plus R of X, we need to show that basically you can regroup this, right? And so what is P of X plus Q of X and then plus R of X, right? Well, that's equal to, we have to unpack what this is. That is, so we have A naught plus A1X plus A2X squared plus B naught plus B1X plus B2X squared in the parentheses. Sorry, I don't like the. And then we're taking that plus C naught plus C1X plus C2X squared. We know by the associativity of the real, like addition over the reals, that is associative, right? So we know that this is the same as A naught plus A1X plus A2X squared. And to be like explicit here, and I'll be explicit. To prove this, you need to kind of have a middle step here, right? You kind of write this just as you drop all parentheses. So you'd have like B naught plus B1X plus B2X squared plus C naught plus C1X plus C2X squared. And then after this step, then you can group the other two, right? But I'll just go ahead and regroup them here. And then what is that, right? We see right away that that is equal to P of X and then plus Q of X plus R of X in the different order. So we've shown that it's associative. What else do we need to show? Well, to wrap up the addition axioms, we have to show that there's the existence of the identity element and an inverse element. So, by definition, we can call it the zero polynomial. So like 0 of X, which is just 0, is an element of P2, right? By definition, you just take A0 or like A equals B equals C equals 0, right? And you get this. Well, then what is P of X plus this 0 polynomial? Like OX, right? Well, this is then A naught plus A1X plus A1X squared plus 0, which is A naught plus 0 plus A1X plus A1X squared, which now we do know that 0 is an additive identity for real addition. We don't know that yet for polynomial addition, right? So we have to take this step to group it with the other constant term here. And now we know that's just A naught plus A1X plus A2. Sorry, there should be a 2 there and there, my bad. A2X squared, which we know is just P of X, which proves that there is the existence of an additive identity. Now, what about the inverse, right? Well, for the inverse, we start by noting that if A0, A1, and A2 are in the reals, then this implies that negative A0, negative A1, and negative A2 are also in the reals, i.e., there exists a polynomial, let's say P bar of X, which is defined to be negative A0 plus negative A1 X plus negative A2 X squared. Now let's take the sum of P and P bar. Well, this is equal to A0 plus A1X plus A2X squared plus negative A0 plus negative A1X plus negative A2X squared. Grouping like terms here, this is A0 plus, or let's just do minus at this point. A0, well, actually, let's not, right? Because we don't have a notion of difference right now. We have a notion of addition and then scalar multiplication by -1. But we're not really assuming a notion of subtraction. We're assuming a notion of additive inverse, right? So this is A0 plus negative A0. We haven't really defined A0 minus. We haven't defined A minus B, but we have defined, because we don't have subtraction as an operation, right? But we have defined addition as an operation and scalar multiplication, and in particular, scalar multiplication by -1. So that's important to note that, you kind of, it's tough to start to realize how much freedom you're losing or how much you can no longer take for granted when you start to step into like these more abstract settings. So what this is going to be then is A1 plus negative A1 X and then plus A2 plus negative A2 X squared. And we do know that over the reals, every element has an additive inverse. And so we get that this is equal to 0, right? Okay, so what we've done is we've shown now that polynomial addition satisfies the axioms for being a vector space. What we need to do now is we need to verify that scalar multiplication also satisfies all of its axioms. So let's go through the axioms of scalar multiplication. The first one was we need to show that it's closed under scalar multiplication, right? And so what do we do here? Let's let K be an element of the reals. And then again, let's use all of our definitions here of like P, Q, and R, right? P was like A0, blah, blah, blah. Q was B0, blah, blah, blah. R was C0, blah, blah, blah. Just so I don't have to redefine these constantly. So if we have K in the reals, and we have P0, we need to see if K times Px is of the form A plus Bx plus Cx squared, right? That's what we have to show. Well, let's see. This is K times A0 plus A1x plus A2x squared, which is, we have the distributive property in real number addition. So this is Ka0 plus Ka1x plus Ka2x squared, which is, grouping by associativity of scalar multiplication over the reals. This is Ka0 plus Ka1 times x plus Ka2 times x squared, which is of the form A plus, right? Here we would have like A is Ka0, B is Ka1, C is Ka2. And so this is then an element of P2, which is what we want to show that scalar multiplication is closed on the set P2. What do we need to show next? We need to show that a scalar distributes. So we need to show if we have K times P of X plus Q of X, we are hopeful that we can prove that it distributes, right? So this is equal to k times, and then a naught plus a1x plus a2x squared plus b naught plus b1x plus b2x squared. We have the distributive property over the reals. So this is k a naught plus k a1x plus k a2x squared plus k b naught plus k b1x plus k b2x squared, right? Now, what are we trying to show? We're trying to show that this is equal to k times p plus q times p. So we've distributed this in the first step, but now we need to distribute in the opposite direction or factor out, but we don't want to just reverse the step we've done here. We want to do this cleverly, right? We notice all of the first three terms here share a factor of k. And so because of that, and because we can factor over the reals, we don't know if we can factor over the polynomials yet, because that's what we're trying to prove. But we do know we can factor over the reals, right? So here we have k times a naught plus a1x plus a2x squared. And then we can do the same thing for the last three terms. So that's k, and then times b naught plus b1x plus b2x squared, which is k p of x plus k q of x. So we have the distributive property of scalars. Now let's see if we have, or we have that scalars distribute over elements of, or over polynomials. Now let's see if polynomials distribute over scalars, right? So now, again, we're going to have k and l. These are going to be elements of the reals. And we want to show that if you take k plus l times p of x, well, that's the same as k times p of x plus l times p of x, right? So what do we get? This is k plus l times p, which is a naught plus a1x plus a2x squared. We know over the reals how to distribute, right? And in this case, it's called foiling, right? Well, it's a generalization of foiling because there's a third term in the second factor there. But what this ends up turning into after you multiply everything, k, not k naught, but k a naught, plus k a1x plus k a2x squared plus, and then you distribute the L, right? So we have L a naught plus L a1x plus L a2x squared. Now what can we do? Now we can factor out a k from the first three terms here. So this is k times a naught plus a1x plus a2x squared. And then we can factor out an L from the last three terms. So a naught plus a1x plus a2x squared, which is k p of x plus L p of x, which shows that the polynomial distributes over the scalars, as well as we know the scalars distribute over the polynomials. We need to show associativity, right? We need to show that if you have k times L of px, hopefully we can show that this is associative. So this is k times L times a naught plus a1x plus a2x squared, right? This is equal to k. And now we know that we have to use a previous property, right? Here we're, well, no, sorry, we're over the reals here. We know what we're doing in the reals. So this is L a naught plus L a1x plus L a2x squared. This is k L a naught plus k L a1x plus k L a2x squared, which we can group as k. Well, we can pull out a KL from every term right? And then we're left with a naught plus a1x plus a2x squared, which is equal to KL times P of X. So we have associativity. One more thing, we need to show that there exists one, right? There exists a scalar multiplicative identity. Well, by definition, 1 of x, which is just 1, this is an element of P2. You just let A be 1, B equal to 0, C equal to 0, right? That's an element, no problem. Well, then let's compute what, sorry, we don't care about that because we're not multiplying the product of two polynomials together. That's certainly not a vector space. That's actually something I challenge you. Prove that if you took, instead of scalar multiplication, you took polynomial multiplication, like P times Q. I want you to prove that P2 addition and then multiplication as the product of two polynomials show that this isn't a vector space. And it's to show it's not a vector space, it suffices to show that somehow, right, nothing's changed here. So what you'll have to do is somehow show that the product of two polynomials does not satisfy at least one of the axioms that we're proving. So I kind of like the mistake I just made there because it led into I think, a really beneficial exercise for you all. So show that's not a vector space. But we do have, you know, 1 is in the reals. Let's compute what 1 times P of X is, right? Well, that's 1 times a naught plus a1x plus a2x squared. This is equal to 1 times a naught plus 1 times a1x plus 1 times a2x squared, right? We don't know if this is a multiplicative identity, but we do know, like for a polynomial, but we do know it is a multiplicative identity for a real number, right? As objects, a naught and P of X are very different objects, right? And so we get that this is a naught plus a1x plus a2x squared, which is equal to P of X, which proves, so QED, this proves that P2 is a vector space because we've gone through the very tedious process of showing that all of the axioms for addition and multiplication are satisfied. There was nothing special about 2 here, like degree 2. You can define P in the same way by saying it's the collection of polynomials like a naught plus a1x plus blah, 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 plus a in x in, you know, such that ai is an element of the reals for all I from 0 to n, right? And this is also a vector space. You can see the proof of showing that P sub n is a vector space would really just be you copy paste the proof that we've just written for P2, but instead of, you know, you just have more terms to carry and more things like that. This is for finite, like this is for infinite, right? What about P infinity, where it's like infinite polynomials? And we understand infinite polynomials, excuse me, as series, right? And we don't write P infinity per se. I mean, you can think about it in terms of this notation, but really what it is, so let's write it like this. This is going to be the set of infinite series where I goes from 0 to infinity of ai x to the I, such that ai is an element of the reals for all I you know, like, so for all I, just from 0, 1, right, all the way to infinity. Do you think this is going to be a vector space? Like, things change when you go from a discrete or finite setting to a continuous or infinite setting. So I have a challenge for you. And I may even, if you were to show me your solution to this problem that I'm about to state, I would consider maybe 5 points of extra credit towards your homework. So if you would like a challenge, and I think this is a very good challenge, I want you to prove or I want you to answer the following question. Is P infinity a vector space? Provide proof of answer. And so I'll say worth 5 points extra credit. If you can answer this question correctly. I mean, I'll give you some points if you attempt it, even if it's not fully correct. I do want to say we don't really write this as like P infinity. How you would see this written is we say R adjoin X. You'd see it like that. So I think that would be an awesome thing to prove, and I think it would really help your understanding of being able to determine what is and what isn't a vector space. I think I'm going to stop for now. What I'd like to do in the next video here is wrap up the kind of introduction and examples to vector spaces. And then what we're going to do after that is we're going to start to go through basically everything we did involving linear transformations in Rn. We're going to go over those notions for arbitrary vector spaces, right? And so we'll look at like, what are spanning sets for the polynomial vector space? What's a basis for a polynomial vector space or for a matrix vector space, things like this. And so after we're done wrapping up like the introduction, definition, examples, some important properties, theorems, what we're going to do is we're just going to go study linear algebra for arbitrary vector spaces instead of just Rn.